Hi everyone, this is Swadhin. Today I'll be presenting our paper RTSense, passive RFID based temperature sensing. This is a joint work with my advisor Lili at UT Austin. Uh, Without further ado, let's set the stage for this work. So why do we need temperature sensing? More specifically, indoor temperature sensing. Like nowadays, due to pandemic, we are spending most of our time indoors. Or apart from this, on an average, we spend majority of our time, around 90% of our time indoors. So fine-grained information of temperature, which is critical for personalized thermal comfort through heating and ventilation system, are needed. And for that, we need to sense temperature at a granular level. Apart from that, in greenhouse-based cultivation, supply chain management, and also in health sector, maintaining the temperature of some items are necessary. And for that, you need to have a temperature sensing mechanism. If that temperature sensing can be achieved through uh, cheap, customizable wireless sensors, it would have been great, and we can make it large scale. So in this paper, we ask this particular question, that can we measure the temperature using passive RFID tags, which are customizable, battery free, cheap, and can also be read wirelessly. More specifically, can you use the impedance change of those RFID tag antennas and map the temperature variation causing it? So, in a nutshell, the question we ask, that can we measure temperature exploiting impedance change due to temperature variation in passive RFID tags? In this paper, we say that yes. And the key idea are the following. So the temperature variation, not surprisingly, changes the tag antenna impedance. And the larger the antenna surface area, which experiences more change. And this impedance change manifests into change of the reflected signal. And thirdly, if we put two tags side by side and exploit the area change between these two tag pair, we can employ differential sensing to sense the temperature. That is the signal difference between these two tags. In this paper, we looked at the phase difference metric, which is a very robust metric even with the environment variation. So we create RFID sense based tag pair, which looks like this, has a bigger surface area with a copper foil and a smaller surface area. And we have also the inbuilt chip connected to these two tags. Here we use the loop tags, which is attached inductively to these tags. And this solution is very cheap, cost around $2. And as I said, as it uses differential sensing, that's why it is robust to change and it is customizable. Now, let's look at how this thing works. So I'll be focusing on the analytical model which we built to kind of justify the design and see how this mapping of temperature variation works. We created a simple dipole tag antenna. So initially we have to create the impedance model for this dipole tag antenna. And next, we have to model the temperature impact on the antenna's impedance. And finally, we have to see how this impedance change manifests into the wireless signal property, in this case, the phase change. If you can model these three things, we can know how the temperature actually maps to the phase variation. So from the literature, we see the RLC model of the dipole looks like this, where the resistance can be given as a function of length, width, and thickness, and also the wavelength of the signal impinging upon it. This has two resistance component, and also the inductance in this dipole tag antenna is also a function of length, width, and thickness. And the capacitance also is a function of the width, thickness, and the permittivity, and also the distance between the two dipoles. And we see this RLC kind of combines in this way, where resistance and inductance are in a series and where capacitance in parallel, and we get a impedance magnitude which is a function of RLC and the omega, which is the function of the frequency. And we then model the temperature change. So as we are looking at the temperature change from 20 degree to 120 degree, in this variation for the specific copper and this dipole design, we observe that the capacitance has almost negligible impact. We also confirm that through measurement both in the ANSYS HFSS software and also the LCR meter. And the resistance is a function of the base resistance component multiplied by the resistivity and the temperature change. And the inductive is also a function of the resistivity, permittivity, permeability, and also the temperature change. And these are the constant for this particular metal, and we know that beforehand. So we can model the temperature change with this variation. So as we see, the larger the width of the antenna area, the larger the impedance change. We measure this impedance through a vector network analyzer, which is an instrument which measures the impedance of any electronic component. So here the impedance change around in the 5 magnitude, where for a smaller 5 centimeter width, it is around 1.5 radian. So next, we wanted to model this impedance change to the phase change. We know the phase is a combination of the distance component, the polarization component, and the impedance component. So here, this is the antenna's GC. GC is the antenna chip's impedance, and GE is the antenna's impedance. So now, as this tag is static, so these two things does not change. So only thing changes the impedance component. So if we look at the differential phase of the two tags, we can get the phase difference as this function, which is the corresponding to the impedances of the two tags. Now, when the temperature changes, the impedance of the antenna changes differently, and we see the phase change. So if we put this previous antenna's impedance model in this equation, we can get a analytical model based measurement of the phase change, and we compare with the wireless phase difference we record in our RFID reader, where we observe that it is very close to our measure at different locations. Now, how we can use this model of phase change due to temperature in the temperature estimation. So we have a very simple model where we normalize our phase change with the change of T mean to T max. This is our measured temperature zone, and we get a calibrated phase pattern over this temperature range at a certain, and we create a polynomial regression, third order regression model on this calibration model, and whenever we get its data of a 20-second data, get the average and put on this equation to reverse map the temperature. So we have the calibrated phase pattern, we measure the phase difference and put that value in our regression model to estimate the temperature. Here I will go over the few of the evaluation before wrapping it up. So for ISO temperature setup, we have this RFID reader antenna and put at a isotemperature oven, and also measure the impedance in parallel, because in outside, if you have to measure that, we can't control the temperature as a whole in the whole surface area. And we have temperature sensor to record it. For outside experiment, we use a heat gun and we create a temperature sensor using Arduino connected to a laptop, which also connected to the RFID reader's antenna to simultaneously capture both the value. Now we kind of change the surface area for a given chip and see how much phase change is observing. We see that larger the surface area, higher the phase change. Now we have to create this two tag pair. If we create a 30 centimeter and 2 centimeter tag pair, where we can observe up to 1.2 degree phase resolution over 25 degree to 85 degree, which is for 2220, it is around 1.8. So the larger area gives you bigger change, but bigger the area after certain time, the tag gets detuned because higher the change observed in the impedance. So now we compare with two related work, which is analog identifier, which is also function of chip power and chip threshold, and a differential minimum threshold power, which calculates the threshold power of the two tags. And also we created a single tag phase difference metric from phi t minus phi 0. And for our RTSense, one was single antenna based. RTSense Multi has multiple antenna, and RTSense FT uses the frequency diversity, which we employ in a USRP into 1004 with multiple antenna to kind of exploit the frequency diversity simultaneously while recording the values. So these are the RTSense is a single antenna, single frequency, narrowband based approach. RTSense Multi is multi-antenna based approach, and RTSense FT is multi-antenna, multi-frequency based approach. So when we plot, the median error in RTSense FT is 2.9 degree, where the closest value is 12.6 of the phase difference based metric, and 6.2 is the RTSense vanilla. So single antenna narrowband approach gives you a median error of around 6.2 degree. We also did some micro benchmark experiments. Some of them are looks like this. For RTSense, the error remains within 10 degree, even up to 3.5 meter, and even we change different orientation, the error remains within 7 degree. So as I said, there are some related work. The two sets of work where we have to create active RFID-based sensing, where we need to have a battery-based sensor with a customized reader, and custom tag antenna-based sensing. We have to create antenna and the reader and the from the scratch. Closest to our work, which we just compare with the differential minimum response threshold, is RFID tag antenna sensing, more specifically RFID hacking in this Mobicom 2019, where they put a thermal register in the tag itself where they measure the temperature. However, as these are power-based metric, these are not robust to multipath, and also as they're putting extra element on the tag antenna, therefore the tag gets detuned very drastically, the range reduced to around 1 meter. So overall, the key takeaways are the following: that antenna surface area can be exploited for sensing, tag pair-based differential sensing can be used for a robust approach against environmental changes, and RTSense can achieve median error of 3 degree, like for the frequency diversity-based approach. For a single vanilla, it gives you around 6 degree. So thank you for your attention. If you have any questions, I'll be happy to answer. So if you want to mail, you can mail to this address. Thank you very much.